Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll discuss some of the gate questions asked for the past exams which are related to torsion of shafts. Let us start with the first question. The maximum shear stress developed on the surface of a solid circular shaft under pure torsion is 240 megapascal. If the shaft diameter is doubled, then what is the maximum shear stress developed corresponding to the same torque? So initially when the diameter is say d, the shear stress is 240 megapascal. Now if the diameter is doubled, then what is the changes in shear stress? What is the maximum shear stress induced on the surface? So you have the torsion equation for a solid circular shaft. T is equal to pi by 16 d cube into tau max. Or from this you can write the maximum shear stress as 16 t divided by pi d cube. So this is the equation for maximum shear stress induced on the surface of a solid shaft. Now suppose if the diameter is doubled, d is instead of d you have 2d. So 2d cube. So that will make it 8d cube. 8d cube. So denominator will get 8 division by 8. So that means initially when the maximum shear stress was 240, when the diameter is doubled, you will have shear stress 8 times less, because denominator you are getting 8 when you double the diameter. So when the diameter is doubled, shear stress will decrease by 8 times, or initially it was 240 divided by 8, the shear stress reduces to 30 megapascal. Now we'll work out the next question. A solid circular shaft of 60 mm diameter transmits a torque of 1600 Newton meter. What is the value of maximum shear stress developed? So torque is 1600 Newton meter, or 1600 into 1000, or 1.6 into 10 raised to 6 Newton mm. Now this is the torque transmitted by the shaft, and diameter is given as 60 mm, and it is a solid shaft. So you have this relation T is equal to pi by 16 d cube into tau max, or tau max is equal to 16t divided by pi d cube, and we substitute for torque this 1.6 into 10 raised to 6 and diameter is 60. You will get the maximum shear stress as 37.72 megapascal. So this is the maximum shear stress developed on the surface. So next, a solid circular shaft needs to be designed to transmit a torque of 50 Newton meter. If the allowable shear stress of the material is 140 megapascal, assuming a factor of safety 2, what is the minimum allowable design diameter in mm? So torque transmitted is given, and maximum allowable shear stress of the material is 140 megapascal, and we are also given a factor of safety. Even the material has got an allowable stress of 140 megapascal. Since the factor of safety is 2, you have to permit only half of this, that is this divided by factor of safety. That should be the permitted stress, in maximum permitted stress in the material, or working stress in the material. So torque given is 50 Newton meter, or 50 into 1000 Newton mm, 5 into 10 raised to 4 Newton mm. Maximum shear stress is 140 megapascal. Even though the material can withstand 140 megapascal, since the factor of safety is 2, we will permit the stress to only 70 megapascal. So tau W, I'll put it as working stress or design stress as 70 megapascal. Now using this as the maximum shear stress, when the torque, this torque is transmitted, we should limit the maximum shear stress to 70 megapascal, since that is the permitted stress. Okay, and the material may withstand higher stress of 140 megapascal up to 140 megapascal, but still we are only permitting 2 times less, since the factor of safety is 2. So using this you can find out the diameter. So torque transmitted is pi by 16 d cube into tau max. Instead of tau max we will substitute the working stress, maximum stress permitted. So using that you will get the diameter as 15.38 mm. So this is the maximum diameter permitted. So out of the choices, if it's given nearest diameter, say 16 mm, you can choose 16 mm. Now we'll work out the next question. A torque of 10 Newton meter is transmitted through a stepped shaft as shown in the figure. The torsional stiffness of individual sections of length Mn, No and OP are 20 Newton meter per radian, 30 Newton meter per radian and 60 Newton meter per radian respectively. What is the angular deflection between the end M and P? So it's a stepped shaft, one end is M, the other end is P. So you have to find out the angular deflection between the ends M and P. So what is the angular twist undergone by the NP with respect to M? The torque transmitted is given 10 Newton meter. So 10 Newton meter torque is transmitted. You are given the stiffness of the 3 sections. The first section, it is 20 Newton meter per radian. Stiffness means the torque required to produce unit angular twist. So this is 20 Newton meter torque is required to produce 1 radian angular twist in this portion. Whereas this is more stiff, 30 Newton meter torque is required to produce 1 radian twist. Similarly, this is a maximum stiffness 60 Newton meter per radian. So you are given the stiffness of the 3 sections, and also you know that torque transmitted by all the 3 sections are same, because torque is only applied at the ends. So all the sections are carrying the same torque, 10 Newton meter. So you can find out the angular twist in individual sections as the torque divided by stiffness, because if stiffness is the torque required to produce unit angular twist, torque divided by stiffness will give the angular twist undergone. So each section you will have torque 10 Newton meter divided by this stiffness, that will give the angular twist in the first section. Similarly, you can find out the angular twist in all the 3 sections, add all the 3, which will give the total angular twist. So total angular twist is theta 1 plus theta 2 plus theta 3. So the angular twist in the first section is torque in that section divided by stiffness of that section. Similarly, torque in the second section divided by stiffness, and torque in the third section divided by stiffness of that section. So that will give the total angular twist. Now the torque T1, T2, T3 are same, 10 Newton meter, and the stiffness are given for the 3 sections. So you will get 10 by 20 plus 10 by 30 plus 10 by 60. Now this is half, and this is 1 by 3 and this 1 by 6. 1 by 3 plus 1 by 6 will make it half. So this part is half, half plus half, you will get 1 radian. So total angular twist undergone by this shaft is 1 radian. Okay. So next question, a solid shaft of diameter D and length L is fixed at both ends. A torque T0 is applied at a distance L by 4 from the left end as shown in the figure given below. What is the maximum shear stress in the shaft? Now, this shaft, which is having a diameter D and length L, is subjected to a torque at this portion, that is L by 4 from one of the ends. It is fixed at both ends and at a distance of L by 4 from the left end, subjected to a torque T0. So this distance is 3L by 4. Now as a result of this torque applied, in this section will be subjected to maximum torque, okay, and this section will be subjected to minimum torque, because this torque applied will offer resistance. This ends has to exert a resistance, so resistance will be in opposite direction. So this is clockwise, so here this should be anti-clockwise. Even this resistance should be anti-clockwise. So the resistance offered by both the sections put together should be equal to T0. Suppose the resistance at this end is T1. So T1 plus T2, that is I have shown here, T1 plus T2, that should be equal to T0. So that is one of the relation. And also we know that at this junction there will be an angular twist. Okay, so this junction will twist with respect to this end, and this junction twist with respect to this end, that should be same. So this twist at this junction is common for this section and common for this section. So if you consider this section with respect to fixed end, this will undergo some twist, and that is also equal to the twist undergone by this section with respect to this end. So the junction will undergo a same angular twist. When you consider either left section or right section, this junction is undergoing same angular twist. So you can equate the angular twist. So this is angular twist in the first section, T1 L1 divided by Jg is equal to T2 L2 divided by Jg. So considering this portion, I am finding out the angular twist of this junction with respect to this end. So it is T1 L1 divided by Jg, and for this section I am finding out the angular twist. Okay, T2 L2 divided by Jg. So that should be equal, or L1 is equal to L by 4, L2 is equal to 3L by 4, and Jg they are equal, so it will cancel out. So you get T1 is equal to 3T2. Okay, so L by 4 also cancels, so T1 is equal to 3T2. So torque here will be 3 times the torque acting on the other end. And here it will carry more torque because it's closer, the torque applied is closer to this fixed end. So T1 is going to be 3 times T2. Also we know that T1 plus T2 is equal to total torque T0. So T1 we already know that it is 3T2. So I substitute T1 as 3T2 plus T2 is equal to T0. So you get 4T2 is equal to T0, or T2 is equal to T0 by 4. So first we got a relationship between T1 and T2 as T1 is 3 times T2. Now I am getting the T2 value in terms of T0. Okay, T2 is T0 by 4. So once you get T2 as T0 by 4, we have T1 3 times T2 or 3 times T0 by 4. So we are getting T1 and T2 in terms of T0. So here T1 is 3 T0 by 4, that is T1, and here we have T0 by 4. So any shaft, any such kind of problems, you can immediately find out the torque like this. Suppose it's a 1 unit length and this is 3 unit length. You can find out the torque here as 3, this is 3 units, total this is 4 units. So 3 by 4, okay, T0 into this distance 3 units divided by total distance 4 units. So 3 by 4. So T0 into 3 by 4 will be torque here. 3 divided by total distance 4. 3 by 4 T0 will be the torque here. Okay. Similarly, this torque here will be, this distance is 1 unit divided by 4 units total. So this T0 into 1 by 4, that will be the torque here. So it is proportional to the distance between the point and the other support. Okay, so if you are finding out the reaction at this support, the distance between the that point and the other support, it's proportional to that distance. So you got T1 and T2. Now the maximum shear stress, we know that maximum torque will be acting this portion. Okay, here you have less torque, so maximum torque is in the first portion. So maximum torque also we got 3 T0 by 4. So we have that maximum shear stress equation 16 T divided by pi d cube, and we know T is 3 T0 by 4. Substituting that 3 T0 by 4, So this 16 by 4 is 4. 4 into 3, 12. 12 T naught by pi d cube. That will be the maximum shear stress. So let us work out next example. A torque T is applied at the free end of a step rod of circular cross section as shown in the figure. The shear modulus of the material of the rod is G. Obtain an expression for D to produce an angular twist theta at the free end. So this is a figure given. Diameter here is 2D and here it is D, and this is a fixed end, and torque is applied at the free end. Okay. As the torque is applied, you have to get an expression for D in terms of the angular twist theta at the free end. So theta is the angular rotation at the free end. In terms of theta, you should get an expression for the diameter. So expression for diameter in terms of the angular twist at the free end. So what is the angular twist at the free end? The angular twist in this section plus angular twist in this section, that will give the total angular twist at the free end. So you have to find out the angular twist in both the sections and add that. That is theta 1 plus theta 2. It is theta. So theta is theta 1 plus theta 2. Theta expression is for any shaft. Theta is TL by JG. J for a circular shaft is pi by 32 d to the power of 4. So that is TL by JG. J value is substituted for polar moment of inertia for a solid circular section is pi by 32 d to the power of 4. So 32 TL by pi d to the power of 4g, that is the angular rotation for a circular shaft, where d is the diameter and t is the torque acting. You can use this formula to find out the angular twist of a solid circular cross section. Now you have to use this equation theta is equal to theta 1 plus theta 2 to find out the angular twist at the free end. So theta 1, that is angular rotation of this portion. Now torque acting is T naught. Same torque is acting on the both the sections. Now T is T naught, substituted as T only. Okay, T naught is the torque acting. So the length of the first portion is L, diameter is 2D. So substituting 32 TL divided by pi into 2D to the power of 4G. Instead of D, you substitute 2D, length is L. So 32 TL divided by pi 16 D to the power of 4G. So 16 will cancel here. So 32 by 16 will make it 2. 2 TL by pi D to the power of 4G. In second portion, you have 32 T into L by 2. L by 2 is the length of that portion, and pi D to the power of 4G. So it will make it 16 TL by pi D to the power of 4G. So it will be 18 TL divided by pi D to the power of 4G. So diameter will be 18 TL divided by pi G theta to the power of 4. 18 T naught you should use, because torque acting at the free end is T naught. So 18 T naught L divided by pi G theta to the power of 1 by 4. That will be the diameter expression in terms of theta. Now let us work out another example. Two shafts AB and BC of equal length and diameter D and D by 2 are made of the same material. They are joined at B through a shaft coupling, while the end A and C are built in. A twisting moment T is applied to the coupling. If TA and TC represents the twisting moments at end A and C respectively, then what is the relation between the torques developed at the ends? So the two shafts AB and BC, they are of diameters D and D by 2 and of same length and same material. They are of same length, same material, and diameters have D and D by 2. Now this is a junction where they are connected. These two shafts are connected by a coupling. So I have shown it as a junction. So there is a coupling here to transmit the torque. and the torque T is applied at this coupling, that is at the junction the torque T is applied, and the other two ends are built-in. Built-in means fixed end, so they are fixed. So once you apply a torque, there will be a resisting torque. So at the end, the resisting torque will be opposite direction. If it's clockwise, this should be anti-clockwise. This is also anti-clockwise. So that is a resisting torque. TA and TC are the resisting torque that will be in opposite direction to this torque applied. Now you have to find out the relationship between the torque developed at the ends. So that it is a relationship between TA and TC you should find out. We know that angular twist in a solid circular shaft is given by TL by Jg, and J is pi by 32 d to the power of 4. So you get 32 TL by pi d to the power of 4 G as the angular twist. And we here, when you apply this torque, the junction will rotate with respect to the other built-in that end. The junction will rotate by an angle. Okay, and this junction with respect to this built-in, the rotation will be same. So the junction rotation either for this section or this section, it will be same. So angular twist for this section AB and for this section BC, that should be same. So theta 1 is equal to theta 2. So angular twist in the first section is equal to angular twist in the second section. And what is the torque acting in the first section? It is TA, that is T minus, if you consider from right side, T minus TC, that should be equal to TA, because total TA plus TC should be equal to T. So T minus TC should be equal to TA. So in the first section, the torque acting is TA. So you can substitute TA, and the length is L, diameter is D. Okay, pi d to the power of 4 G. In the second section, torque is TC, but diameter is half, D by 2. So diameter is D by 2. So D by 2 means here 1 by 16 will come. So it is 16, 1 by 16. The rest of the things are common. Pi d to the power of 4G, pi d to the power of 4G, pi d to the power of 4G. Here 1 by 16 will be there. L cancels. You get 32 TA. You get 32 TA is equal to 32 TC divided by 1 by 16. Or 32 cancels. TA is equal to 16 TC. So the torque developed at this fixed end will be 16 times the torque developed at C. This end will be subjected to maximum torque. So this portion will be subjected to maximum torque as a result of this torque applied at this junction. That's all for today. Thank you for watching.